For years, scientists assumed Mount Etna's greatest danger came from its eruptions, but then they discovered something far more unsettling. The entire southeastern flank is sliding toward the sea, not pushed by magma, but dragged by gravity itself. In 2017 alone, 4 centimeters shifted in just 8 days. No quake, no warning, and the scars offshore reveal it has happened before. So how did one of Europe's most iconic volcanoes become a silent geological time bomb? What hidden weakness in its ancient foundation makes this movement impossible to stop? To understand the truth, we have to look beneath the surface. Beneath Etna's towering slopes, the ground is nothing like solid rock. The entire southeastern flank rests on ancient marine sediments, soft water-rich clays, and loose volcanic debris accumulated over thousands of years. Near the coast, these layers can be just 10 meters thick, but offshore, they deepen to nearly 50 meters. Instead of acting like firm bedrock, they behave more like a saturated sponge. Laboratory tests confirm their weakness. Porosity can rise to 70%, and shear strength may fall as low as 10 to 20 kilopascals. Under a mountain rising more than 3,000 meters above sea level, that means the foundation can deform with remarkably little force. A structural geologist compares it to stacking a tower of books on a pillow. The heavier the load, the more the pillow spreads outward. Etna's massive weight pushes down and out in every direction. The sediments below cannot resist forever. They compress, shift, and allow the entire southeastern flank to move sometimes only millimeters a year, but always toward the sea. The instability does not stop at the shoreline. Seismic reflection surveys and sub-bottom profilers reveal that these weak sediments stretch beneath the Ionian Sea, forming a continuous slippery base that links Etna's on-land flank to the submarine slope. Deep borehole logs confirm that even offshore, the sediments remain highly porous and low in strength. Pore pressure measurements show fluids trapped within the clays can build up, reducing friction even further and making slip easier. The result is a mountain perched on an unstable foundation, a slow-motion landslide driven not by eruptions or quakes, but by the relentless pull of gravity on a yielding base. Every centimeter of movement is tracked by a network of sensors. Yet the real story begins deep underground, where the ground is simply too soft to hold back the mountain's weight. On Etna's eastern flank, a massive scar stretches 5 kilometers wide and drops more than a kilometer deep. This is the Valle del Bove, an immense amphitheater not carved by slow erosion but created by a catastrophic collapse thousands of years ago. Geological records and offshore sediment cores match the debris from that ancient event with remarkable precision. Disturbed layers of marine mud, volcanic fragments, and sand found on the seafloor align perfectly with material swept into the sea during the collapse, a signature found nowhere else along Sicily's coast. Radiometric dating places the catastrophe around 8,000 years ago, when a section of the volcano's flank gave way and millions of tons of rock and ash tumbled downhill and into the sea. Marine surveys reveal enormous debris fields spreading across the seafloor for kilometers beyond the present shoreline. These chaotic layers, known as turbidites, appear only after major slope failures. Sediment cores show a sharp boundary calm mud below a violent jumble of rubble above, all deposited in a single event. Local folklore still echoes with distant memory of a night when the mountain roared and the sea rose, blurring story and history. But geology leaves no doubt. The Valle del Bove is the mark of a mountain that has collapsed before. Historical geologists have reconstructed the sequence of that ancient disaster. First came seismic tremors that fractured the flank. Then, weakened by gravity and the soft marine sediments beneath the slope, finally failed. The collapse unleashed a torrent of debris, racing downhill at speeds that may have reached hundreds of kilometers per hour. In the aftermath, the enormous depression reshaped Etna's entire eastern side, while the debris field on the seafloor became a permanent testament to the volcano's instability. The sheer scale of the Valle del Bove, spanning 5 kilometers across and plunging more than a kilometer deep, is a stark reminder Etna's slopes have failed catastrophically before, and the evidence lies both in the scars above ground and the buried chaos offshore. For scientists watching today's slow slide, these ancient events are not distant history. They are proof of what is physically possible and what could happen again. In May 2017, a team of geophysicists in Catania and Kiel gathered around their monitors, watching real-time acoustic readings from sensors anchored deep beneath the Ionian Sea. Installed the previous year along submerged faults east of Etna, these instruments were designed to detect even the smallest shifts in the underwater slope. For days, the data showed nothing unusual: background noise, minor tremors, the steady pulse of the sea floor. Then the numbers changed. Over just 8 days, the entire submarine flank slipped 4 centimeters eastward. There was no eruption, no earthquake, no summit warning. At first, the lead scientist, Dr. Marilia Earle, suspected a calibration error, but the signal appeared across every baseline. The movement was real, and it was silent. Field notes from that week captured the shock. May 12th, acoustic baseline anomaly, no seismic event. Flank slipped 4 centimeters. Internal emails rushed between stations, each message carrying disbelief. For decades, scientists believed magma pressure drove Etna's shifting slopes, but this event showed otherwise. No magmatic intrusion, no summit deformation, only gravity. Earle later explained that they had always assumed magma was the cause. This single event proved that gravity alone could trigger a flank failure. And the implications were enormous. The entire southeastern sector, including the portion hidden below the waves, was moving as one massive block. The 4-centimeter slip in just 8 days was unprecedented both in speed and in cause. It defied every expected warning sign. No seismic spike, no eruptive activity, no visible deformation on the surface. It forced scientists to rethink the mechanics of volcanic movement. If a flank could shift this quickly without any magmatic trigger, then monitoring gravity-driven motion became just as critical as tracking eruptions. Inside a dim control room outside Catania, a technician studies a wall of monitors displaying real-time data. More than 100 ground stations across Etna's slopes and coastal plain feed constant streams of GPS readings, microseismic vibrations, gas concentrations, and radar measurements. Offshore, dozens of acoustic transponders and pressure sensors map the submarine flank, relaying their signals through fiber optic cables to the surface. Every few seconds, the system updates, capturing the mountain's drift down to the millimeter. Clusters of GPS stations on the southeast flank track both horizontal and vertical displacement. Seismometers buried along key faults and inside deep boreholes register tremors too faint to be felt at the surface. Ocean-bottom hydrophones record pressure shifts as the underwater slope flexes. And satellite radar makes routine passes overhead, confirming the ground-based measurements with sweeping images of deformation across the entire volcano. After the explosive eruptions between 2021 and 2025, strain data show a subtle but persistent increase in movement across the sliding sector, especially after the June 2025 swarm. Where the flank once crept steadily, instruments now detect sharper pulses of motion, sometimes several millimeters in a single week. Patterns cluster after volcanic unrest or heavy rainfall, suggesting the slide responds to both deep and surface triggers. All of this information converges in the control room, where scientists and civil protection officials meet daily to interpret the latest trends. Though the average drift is still just a few centimeters per year, the system is built to detect even the slightest acceleration. As one technician puts it, every tremor and every millimeter matters. Their mission is simple: understand what the mountain is doing before it becomes a crisis. For Etna, the most advanced monitoring network on any volcano is both an early warning system and a constant reminder. The mountain is always moving, and none of that motion is left to chance. On a quiet morning in a research lab near the Sicilian coast, a tsunami modeler loads a simulation few outside scientific circles ever see. The screen floods with color-coded waves racing across the Ionian Sea, each born from a scenario no one wants to face: the sudden collapse of Etna's southeastern flank. In the worst-case model, billions of tons of rock break free in a single violent event. The mass plunges into the sea, displacing water on a scale unmatched in living memory. Within minutes, waves 20 to 30 meters high crash into the Sicilian shoreline. Towns like Reposto Aci Trezza and the Catania Port District disappear beneath the surge. The numbers are stark. Wave heights rival those of the 2004 Indian Ocean tsunami. But the time to impact is even shorter. For eastern Sicily, the warning could be measured in minutes, not hours. The modeler scrolls through a list of potential triggers: a major offshore earthquake, a sudden magmatic intrusion deep below, weeks of intense rainfall saturating the already weak marine sediments. Any one of these could push the system past its breaking point. While the average movement of Etna's flank is slow and predictable, the simulations show that under the right combination of stresses, collapse could occur almost instantly. In that worst-case scenario, the consequences are absolute. Tens of thousands of lives and entire coastal communities would be at risk. But the modeler does not stop there. Next come simulations of staged collapses where only portions of the upper slope fail. These events are far more likely and less dramatic, yet still dangerous. Each partial collapse sends debris rushing into the sea, generating waves that may not reach the height of a mega tsunami, but are still powerful enough to flood harbors, beaches, and low-lying neighborhoods. The numbers for these incremental failures are less precise. While catastrophic collapse could produce waves up to 30 meters, staged events might generate surges of several meters easily enough to swamp boats, damage ports, and threaten anyone near the shore. Scientists acknowledge this gap in data and are working to refine these models. For now, civil protection teams must prepare for both extremes. The modeler pauses at one critical point. The difference between worst-case and likely scenarios is not theoretical. Emergency plans, evacuation routes, and public education campaigns depend on these projections. While the catastrophic scenario draws headlines, most experts consider partial collapses more probable. Yet even those could trigger local disasters if warning systems fail or evacuation routes become overwhelmed. In the coastal towns facing Etna, daily life unfolds under the quiet weight of this knowledge. In Riposto, shopkeepers sweep their doorways and glance toward the horizon where the mountain rises behind them and the Ionian Sea stretches out ahead. The slow drift of Etna's flank just centimeters each year is invisible but never forgotten. At the Civil Protection Office, staff track bulletins from the INGV monitoring network. Evacuation maps are updated and instructions are posted in schools and harbors. Over the last decade, emergency drills have become part of the school routine. Children practice the fastest route inland away from the shoreline, carrying laminated cards with emergency numbers. Teachers explain the sirens that sometimes echo across the rooftops. Scientists describe the current movement as dynamically stable, not safe, but holding together for now. The mountain is moving yet slowly enough that there is no immediate threat. Fishermen keep radios tuned to emergency channels. One of them, Salvatore, says they trust the scientists. If the mountain speeds up, he believes they will hear it on the radio long before they see it in the waves. Civil protection teams work from playbooks built around real-time sensor data. GPS stations, seismometers, and ocean bottom pressure sensors feed into a central command center where technicians watch for sudden acceleration. If instruments detect an unusual slip or a cluster of tremors, automated alerts flash across municipal dashboards. Protocols are straightforward. If movement crosses a critical threshold, sirens activate across the coastal plain and evacuation orders go out by text radio and loudspeaker. In some towns, volunteers rehearse their roles each spring, guiding traffic, assisting the elderly, and helping families reach higher ground. Other communities struggle with limited resources or gaps in the siren network, relying on word of mouth and the hope that warnings will come in time. Still, uncertainty lingers. The timeline for a major collapse is unknowable. It could be centuries away, or it could start with almost no warning. Unlike eruptions, which often give days or weeks of signals, a gravity-driven slide might accelerate in hours, brought on by heavy rain or a distant earthquake. For residents, preparedness matters more than prediction. Awareness campaigns encourage families to keep go bags ready and to memorize evacuation routes not just for eruptions but for potential tsunamis. The goal is not to forecast the exact moment of crisis, but to ensure that if Etna moves faster, the people below can move too. In markets and along the waterfront, there is a quiet acceptance of the risk. A local teacher puts it simply, "They love this place, but nothing here is permanent." The mountain offers warnings if people are willing to listen. Right now, Etna's flank shifts only centimeters per year, almost silent yet unstoppable. Instruments record every movement, revealing a system defined by slow pressure, ancient weakness, and the constant pull of gravity. More than 900,000 people live within reach of its shadow, and the waves a collapse could send across the Ionian Sea. Nature's timelines are not our own. The ground beneath us is never as fixed as it feels, and sometimes waiting itself becomes the clearest warning. What that uncertainty means depends on a single question: how prepared are we when the mountain decides to move?